Singapore's Marina Bay Sands is one of the world's most complicated construction projects. Engineers have to build not one, but 3 skyscrapers that will shoulder a sky park as big as an aircraft carrier.
Worst case scenario, we get stuck.
They have to devise ingenious solutions to assemble a 60-meter tall museum of impractical dimensions, install giant artworks, and erect seemingly floating pavilions for shopping and entertainment. If engineers succeed, they will create a virtual city unto itself. Singapore, the Southeast Asian country, is smaller than New York City. The lack of space forces it to build its largest leisure and entertainment hub to date on a small tract of reclaimed waterfront land. The Marina Bay Sands. It's not one megastructure, but many. Serious challenges lie in the array of buildings that form the unique complex. 3 57-story hotel towers slope at such great angles, they're in danger of buckling under their own weight. An even bigger problem is the hotel's roof. A 340-meter sky park spans its length, containing gardens, outdoor pools, and the world's largest cantilevered observation deck. But how do you build something as big as an aircraft carrier, 200 meters in the air? In the hotel's atrium, mammoth works of art have to be somehow incorporated into the architecture. Its challenging centerpiece, a 15-ton mass of steel by a renegade artist from Britain. A 60-meter tall art science museum is designed for maximum visual impact. It will be to Singapore what the Opera House is to Sydney. Only one problem. It seems too impractical to construct. And a set of dramatic glass-encased pavilions, while themselves pose little challenge, have to be built in water. The man behind the Marina Bay project understands the risks, but he believes that anything short of astounding will fail. Sheldon Adelson, one of the world's richest men and CEO of Las Vegas Sands Corporation.
What we hope to accomplish is to change the face of Singapore tourism. So we expect a very successful development. That is by far the largest and most expensive single project we've ever undertaken. It'll cost about 5 to 5.5 billion US dollars. It's a lot of money. Now, I know $1 billion doesn't buy what it used to, but by any measurement, it's a lot of money today.
Adelson believes his huge investment is safe in the hands of Moshe Safdie, a world-renowned architect. Safdie is recognized for his use of dramatic curves and geometric patterns. The Marina Bay complex will be his largest and most difficult project yet.
I think that architecture has to be timeless. Therefore, what it espouses, what it provides, needs to be something that has a long life. What's unique about Marina Bay is all the pieces coming together. You can't think about it as individual buildings. You've got to think about it as a piece of city. It's much more a symphony than it is a sonata.
On the ground, engineers are more concerned about the reality of building Safdie's vision.
This is the North Retail section area.
30-year veteran John Downs is in charge of overseeing the entire project.
The design is very, very diverse, and each component of the project is totally different from the others. For a project of this size, you'd expect with the planning, with the design, with the construction, you'd be expecting somewhere between 6 to 7 years. Here is basically a 3-year turnaround.
The first and most critical construction task is to secure the footprint, though this normally straightforward job proves otherwise. Since the site was originally allocated for boats. The complex sits on 560,000 square meters of reclaimed land, part of a decade-long plan to revamp Marina Bay, a former saltwater estuary that's now a freshwater reservoir. Beneath the reclaimed land, which is essentially a seabed, is a dangerous layer of marine clay. Sometimes called black toothpaste, marine clay has very poor structural properties. If not given complete respect, the unstable marine clay is potentially fatal. In 2004, Singaporeans discovered the lethal consequences firsthand. A routine excavation in an underground tunnel for the mass rapid transit network causes a collapse, creating a gaping hole in the nickel highway, killing 4 workers.
The ground conditions in which they were building the nickel highway were not dissimilar to those in which we are encountering here. They had also soft clay. They had similar depths of excavation between 20 and 37 meters. One of the big things that was learnt in the nickel highway collapse was the importance of monitoring movements and the control of quality as the construction proceeds.
Marine clay is an old foe of engineer Mike Barton. He's defeated it in the past by understanding how it behaves.
The big problem with marine clay is that it is so soft that when you dig out the inside, the walls will move and potentially collapse and allow all the surrounding water in the bay into the excavation.
So, before work can begin, the unstable building site needs major fortification. To combat marine clay, engineers decide to build giant concrete walls to create stabilizing perimeters for the larger buildings, known as diaphragm walls. Up to 1.5 meters thick, diaphragm walls are steel-reinforced concrete sections, pounded 50 meters into the ground. They form watertight enclosures for men and machines to work round the clock. In just 1 year, over 4,000 meters of diaphragm walls help produce a rock-solid foundation.
The diaphragm walls that we constructed in a formation which we called a peanut formation, which is 2 circles joined together, and a donut formation, which is circular, is that they are able to withstand very, very large forces from the marine clay without any movement. They encapsulate an area that's bigger than a football pitch that enables us to excavate very quickly and to build structure up very quickly.
Securing the footprint of the Marina Bay project has already taken a year out of John Downes' schedule. He now faces the difficult task of erecting the resort's many buildings in a space of just 2 years.
Just managing the whole logistics of that, including the construction methodology, is very, very challenging for us.
1, 2, 3.
To meet his tight deadline, Downes chooses the most direct solution. He hires 16,500 workers to construct every single building, simultaneously. It's like leading a small army. So organizational excellence is key.
We're just on the edge of Singapore in the CBD here, So rather than lose the contractors and the workforce to go off-site, we built our own 3-story project office. We have all of our contractors, our subcontractors here. We house our resident site staff. We have our project management team. We have our construction management team, our design management team, and the logistics here.
The tight schedule also creates problems at the hotel towers, where engineers are already struggling with a congested site.
The important thing to do is to make sure that they come in and deliver the goods straight away and then get out again. We don't want too many vehicles on site at the same time.
To speed up construction and alleviate traffic congestion, engineers turn to a method that's proven itself countless times in the field: in situ concrete casting. Hotel walls are made on site in the thousands. And workers laying the floors are so proficient, they produce 1 floor per 4-day cycle. It's an impressive display for a conventional solution. But the structure they're attempting is anything but conventional. The key challenge of building the hotel towers is its unusual design. Unlike other skyscrapers, part of the towers slope at incredible inclines. Like a set of collapsing dominoes, the towers could buckle under their own weight if a practical building solution is not found. It's a major concern for engineer Craig Glover.
I've been in the industry for 25 years, done a wide range of projects in many different countries, but nothing compares to this whatsoever. There was nothing we could take reference from across the street, on the next high-rise, or across town. This is a new frontier.
Costing a staggering $5.5 billion to build, the Marina Bay Sands could be one of the world's most expensive mistakes if engineers can't solve the tower's problematic structure. Engineer VC Cheong leads the design team, and their solution comes out of left field.
If you look at the configuration, it's not a straight tower. It's with a sloping leg. So all this sloping leg actually is, inducing a very huge external force onto the structure. We cannot build it without any support. So we actually formulate a solution to prop up the sloping edge.
Using a technique they've never employed before, engineers build large temporary struts made of strong structural steel. They prop up the sloping towers as they rise. Like a suspension bridge, high tensile steel tendons, also known as tension cables, give an added layer of support inside the walls. In theory, both the struts and the tension cables are temporary and will be removed once giant link trusses connect the towers at the 23rd floor. The sheer weight in concrete is enough to topple the towers at level 8 if the engineer's calculations are wrong. To reduce the chances of failure, Glover and his team make a radical decision. Instead of removing the temporary tension cables in the tower walls, they make them permanent supports.
I feel good it's in there because it's added strength, it's added support. We have a twined network here of high-strength steel. And what we do is we bundle these up so they form a cord with multiple strands inside this conduit. We place this conduit inside the walls prior to casting the concrete. So what we then do is once the concrete is cast, we anchor one end into the concrete. So we then put a very high-strength pneumatic jack onto the collar and one by one pull these strands through and tension them up. What that does is basically pull the building back and hold it in place. If these cables were to suddenly break, or if they weren't in place, we wouldn't be able to control the self-weight as we build more and more of the building up.
Despite the team's quick thinking, The true test of their engineering decisions will only happen once the main support struts are removed and the massive link trusses installed. Link trusses are huge reinforced steel brackets that bind the towers at the 23rd floor. Once their installation is complete, they transfer the sloping tower's weight completely away from its temporary struts.
Once we're satisfied that we don't have any stability issues, then we can bring the large hydraulic cranes in and member by member start to dismantle the struts. We've got a lot of time pressure, so we've just got to make sure that these things keep moving.
As the last pieces of support struts leave the site, Glover and his team can finally breathe a sigh of relief. The link trusses are holding the building load. So far, so good. Not all the structures have ended up according to plan. The 60-meter-high Art Science Museum is facing a major design overhaul. Planned as a venue for blockbuster exhibitions on the arts and sciences, its bowl-shaped roof doubles as a 3,000-seat amphitheater. Unfortunately for engineers eager to start its construction, architect Moshe Safdie isn't happy with its current shape.
Somebody looked at them and said, looks like a bunch of bananas. In fact, Mr. Adelson said, looks like a bunch of bananas. I said, well, if they look like a bunch of bananas, we're not there yet.
It's terrible news for Safdie's design team, especially its principal, Gene Dyer.
There are times that Moshe will come in with an idea. We think it's quite exciting. We'll pursue the idea for weeks or even months. He'll come back and say, I want to change the idea. And we've already bought into the idea, so it's a bit frustrating.
To rework the unique geometry and dimensions of the Art Science Museum, Dyer and his team turned to advanced 3D modeling programs. It not only makes navigating the museum's complex geometric patterns easier, it shortens the process to a matter of days.
The model is dynamic and it can be moved by just changing one or two elements. Moshe could experiment. He could make rapid judgments in a very short period of time about which way he wanted to take the project. This is a process that was impossible to do 10 years ago. Without the computer, this would take years and years and years.
After months of refining the design, Safdie is finally happy with the result.
The mathematical precision that we gave them made them even more beautiful. It led some people to say, well, hand of welcome. Others said, is that a lotus? And the more ambiguous the associations, the closer I thought we were getting to our target. Because I think the least exciting buildings are those which have overt symbolic associations.
Armed with the new design, engineers begin work on the museum's 60-meter-high superstructure. A staggering 5,600 steel elements, weighing some 5,200 tons, are prefabricated to exact specifications. They are then trucked onto site and assembled. It's like putting together a giant jigsaw puzzle. Each element has to be installed with pinpoint accuracy. If it's even a few millimeters off, engineers will have to start from scratch. Engineers of the massive atrium at the base of the towers are facing an equally tough construction process. Safdie has come up with a challenging design. He wants to inject art into the atrium's architecture, so that visitors will feel like they're walking through a grand Gothic cathedral.
In medieval times, if you think of a Gothic cathedral, there's the architecture, there's the stained glass windows, there's the sculptures on the pinnacles. You cannot draw a line and say art and architecture. Art and architecture are one, they're singular experiences. And I think what we try to do here is come back to this integrative mode.
To create the centerpiece of his vision for the atrium, Safdie commissions renowned British sculptor Antony Gormley. Famous for his unusual approach to art, Gormley is the brains behind the Angel of the North sculpture in northern England. What he's about to attempt is proving to be more of a construction challenge than an artistic one. A cloud-like sculpture some 40 meters long, made up of 15 tons of high-grade stainless steel, hung 12 stories above the atrium.
The Angel of the North is, in a way, making a very traditional public sculpture because it's isolated in space at the edge of a valley. You can see it for miles and miles. It's very much about occupying space. This is about activating space.
But just as they're about to begin construction, a bombshell drops. September 2008, a global financial crisis wreaks havoc on markets. The flow of the hundreds of millions of dollars that keep the Marina Bay project going every month suddenly stops. For engineer Matthew Pryor, it's a massive blow.
I feel devastated. I mean, it couldn't be worse. Probably the worst day of my life professionally. There's no more money coming through. So unless we put some funding in place or there's something, we're going to have to shut the jobs down. It is a tough decision to be made, and we don't know what we're going to do just at this point in time.
With the future of the multi-billion-dollar project plunged into doubt, all eyes turn to the man behind it, Sheldon Adelson. The next move of one of the world's richest men will determine the fate of the mega construction site. The 2008 global financial meltdown is a haunting echo of the 1990s Asian crisis. Back then, progress on Shanghai's World Financial Center came to a complete halt for 5 years. For Adelson, that's simply not an option for the high-profile Marina Bay resort. His vision of changing the face of Singapore tourism is at stake. And so are billions of dollars of investment from his Las Vegas Sands Corporation. He prefers finding a stopgap solution to weather the storm.
Throughout history, there has never been a trend that went straight up, nor a trend that went straight down. So it goes up and down. It's only a matter of time when things will recover.
In a bold move, Adelson pledges his vast personal wealth to the completion of the project, effectively ending any speculation of failure.
There's a massive sense of relief in the company. I mean, everyone pleasantly surprised how quickly we've got through this and the fact we could hold it together and get it going again. So euphoria is probably the best way to describe it.
With the crisis averted, construction on the 3 57-story hotel towers, the casino, theaters and convention center resumes at pace. Everywhere you turn, steel is being installed. It's vital reinforcement for every concrete structure on the 15.5-hectare site. For one project at the tower's atrium, steel is more than just reinforcement. To construct the 15-ton drift sculpture by British artist Antony Gormley, engineers had to first laboriously prefabricate it into over 70 segments. The segments are then welded into 8 slices and will ultimately form the sculpture. It's a tricky operation, but engineers are able to complete it swiftly due to a system of codes and numbers that enable them to quickly identify what goes where. Once all 8 slices of drift are fully assembled, it's lifted up into position by a temporary lifting frame. A massive box truss on the atrium ceiling then takes over the load. In theory, the box truss will support the weight of the lifting frame as it's being lowered down. It will be a heart-stopping moment, especially for engineer Graham Stevenson.
The lifting frame is about 9.5 tons, so when it picks up and gets some momentum, there's a potential that it just wants to flick over and rotate through its full 90 degrees, and we won't have it under control.
Stevenson's solution: 4 powerful automated hoisting drums located at the 4 corners of the frame. They allow workers to control the strength and speed of the operation with high tensile steel cables. A spotter at the top determines the pace of the procedure and marshals the team. The entire operation is estimated to take up to 10 hours to complete. As soon as the frame is in motion, there's no turning back. Midway through the lift, Stevenson receives reports of a potential problem.
22-story, number 7 temporary cable, scaffolding touching the cable. Why you got the temporary cable touching to the transverse?
Yeah, but is it just the end of a tube?
Yeah.
So you can just cut the tube?
Yeah.
Problem solved. But what was previously an estimated 10-hour procedure now turns out to be a 24-hour marathon lift. At 6 a.m. the following morning, they complete the job.
Absolutely fantastic. The Gormley is now finally in its final position, so really an end of a long and exhausting day, and big thanks to everybody, but it's finally done.
While the drift settles into its new home at the hotel atrium, elsewhere attention is focused on one of the project's key features: the Crystal Pavilions. The 2 glass-encased buildings by the promenade are set to be the resort's premier shopping and entertainment complexes. But before engineers can make them a reality, they have to secure their footprint. And already a major obstacle threatens to sink their objective. The Crystal Pavilions are situated within the confines of Marina Bay. So to found it, engineers have to find a way to build in 6 meters of water. The responsibility of tackling the problem falls on the shoulders of engineer Kurt Vella.
I'm from Sydney. The underlying foundation in Sydney is sandstone, it's rock. All you need to do is just dust off the surface and you can build skyscrapers on it. Here it's very different. All the structures have to be heavily founded.
To keep water out of the construction site, only one solution seems viable for Vella and his team: a waterproof steel structure called a cofferdam. This temporary formation surrounds the worksite with a circle of steel sheet piles, creating an impenetrable shield that locks out the water, keeping the workers safe within. For the job, they rope in a 12-ton vibro hammer. It punches the sheet piles deep into the earth, making the cofferdam rock solid and resistant to movement. With the cofferdam secured, engineers deploy powerful diesel pumps and run them 24 hours a day. ejecting any water that remains within the walls. This last step comes with inherent dangers. The force of the water outside creates what engineers call hydrostatic pressure. In theory, it's powerful enough to force water through any gaps in the cofferdam. It's something that Vella prays will not happen.
There's a bit of hesitancy and concern because we've got to build this building in the middle of Marina Bay. Everybody can see what we're doing, so if it leaks, it's a problem. If it fails, if it moves, if it collapses, it'll be an absolute catastrophe.
After a day of pumping, Vella's worst fear comes true. Parts of the cofferdam are leaking. To rectify the problem, Vella orders a team of 8 divers into the water on 10-hour shifts. Their mission? Find out where the water is being forced in and plug them shut with epoxy resin. Anson Lee is an 8-year diving veteran.
The toughest part of my job is the environment. The visibility is poor here. It's totally zero. I cannot see anything here below. I solve that by feel the suction and then feel out the thing. You have to overcome all the fear that you can't see under the water. But okay lah, I feel proud to be one of this team to build this thing out.
After 2 weeks of hard work by divers and the pump crew, the job is finally complete. After 2 years of battling the elements and overcoming difficult construction milestones, the 3 sloping towers of Marina Bay Sands can finally celebrate their topping off ceremony and move on to the next phase. But a destructive force of nature threatens to throw a spanner in the works. With climate change predicted to affect the pattern of Southeast Asia's typhoons, Singapore may one day experience the destructive tropical storms plaguing its northern neighbors in the Philippines and Taiwan. When that happens, typhoon-force winds could spell disaster for the hotel towers, especially the 340-meter sky park sitting on top of it. The force of the wind can make both buildings sway dangerously, causing irreparable damage to the structures. The Sky Park, offering 360-degree views of Singapore. The visionary design will have enough surface area to park 4.5 Airbus A380s. But when architect Moshe Safdie first mooted it, it stemmed from a purely functional need.
Luxury hotels, as we think of them, always have lots of open space around them, gardens, at least in the kind of tradition. But we didn't have much space left. And at that point, I figured, well, if we cut out of an extrusion of foam the kind of slab that goes over those 3 towers, and we placed it there, and we said, well, what do we have here? My God, that's some park. And so that's where the idea was born. That's what makes us a resort.
This is not a critical direction.
Safdie's revolutionary idea scores points for ingenuity, but it clearly isn't what nature intended. Typhoon-force winds threaten to rock the towers and its sky park, causing unimaginable damage. If engineers are to make the building a reality, they'll need a rock-solid solution.
Still got to do all this planning.
Engineer Tony McKee has little time to make things happen.
At the moment, we're running a couple of weeks behind what we'd originally planned. We're not entirely happy about it, but at the end of the day, we've got to do this safe and we've got to do it properly. You're safe, close to
To fight the enemy, McKee knows he has to first understand the enemy. He hires leading US wind engineers CPP to carry out extensive testing on the towers and Sky Park. Their mission? Find out how Singapore's potential wind forces affect the buildings. Wind engineer Roy Danoon oversees the process at their state-of-the-art wind tunnel in Fort Collins, Colorado.
The thing that makes this really special is the fact that we have this Sky Park running across the top, linking all the towers together. So whereas normally with a normal tower, we'd measure the loads on the tower in isolation, with this one, what we're needing to do is to measure the loads on all three of the towers at exactly the same time. So that way we can know how the towers are going to move relative to each other, so we can make sure that they're not going to put excessive strains or movements into the Sky Park.
During the tests, a scale model of the Marina Bay Towers is blasted with 40km/h winds to simulate faster typhoon winds in reality. Over 1,000 pressure measuring instruments inside the model register how the winds affect the buildings. At the end of the tests, engineers confirm that the three towers can deform by some 200 millimeters during the fiercest storm. Engineers quickly figure out a solution: movement joints. Inspired by bridge engineering philosophy, movement joints are essentially gaps located between the concrete towers. The huge gaps allow for movements of up to 250 millimeters. Aluminium and stainless steel plates act as sliding components.
They can move back and forward over each other, a little bit like you'd see in a flexible bus, where you have that articulation happening in the middle. It's a similar concept to that.
To accommodate the differing movements of the three towers, engineers install multi-directional steel bearings below the Sky Park. Armed with the final results, McKee can now safely begin construction of the Sky Park. Consisting of some 10,000 tons of steel, the Sky Park is as big as an aircraft carrier. The most practical way for engineers to construct it is to break it into 14 segments on the ground before assembling it at the top of the towers. There's no room for miscalculation at 200 meters in the air. Each segment is carefully prefabricated and tested by steel specialists Yongnan, and then trucked to the site independently. From the very beginning, McKee and his team anticipate that their biggest challenge will be lifting the two largest segments of the Sky Park, the box girders. Measuring 80 meters long, their combined weight is a staggering 1,400 tons.
How do we feel? A little bit of apprehension. You know, it's a significant lift that hasn't been done before. If something goes wrong, it could be really significant for us.
To reduce risks, McKee turns once again to proven bridge building technology. In a process known as strand jacking, giant temporary lifting gantries made of strong structural steel will use powerful hydraulic jacks to lift the box girders up to the top of the towers before sliding them into place. It will be the longest and largest lift of its kind in the world, and McKee needs the best in the business. He puts a pioneer in the field in charge. Swiss-French company VSL. Engineer Eddie King and his team have successfully raised bridges, stadium roofs, and even Ferris wheels.
The toughest work of my work is you have to plan it everything very precisely, because everything to set up in millimeters. So we have to lift up and slide it in and position it in 5 or 10 millimeter accuracies. we don't do properly or don't do safely, yeah, the biggest hazard is the thing can fall down to the ground.
Other factors further complicate the lifting process. Due to an increasingly tight schedule, the team is forced to conduct the lift during Singapore's annual monsoon season. It's almost impossible to predict when a tropical storm will hit. When it does, the accompanying lightning strikes can endanger lives. And because the whole operation takes place meters from a jam-packed highway, curious onlookers will be able to see any mistakes the engineers make. It's a potential public relations nightmare.
Okay, now I stop now.
During an estimated 16-hour lift, the box girders will move at a cautious 14 meters per hour. Eddie King and his team constantly check their weather gauges for any incoming storms. The hydraulic jacks are also inspected regularly for overheating. No one wants the operation to stall in mid-air.
0.1 to 0.4.
288.
Oh, that one, this one. Change to channel 2, yeah?
Despite the team's best efforts, Mother Nature catches them by surprise.
Okay guys, rain is coming. It's better we stop here.
An approaching downpour threatens to grow into a lightning storm.
We are at 200 meters above and surrounding building is quite far away. So there's a chance of the lightning striking on the high point like this. So we got to stop and wait until the weather getting better before we continue our lift.
McKee's worst fear comes true. If the girders remain stuck at midway for too long, he will have to order them down.
Okay.
After a tense 3 hours, the lightning threat passes, and the operation cranks back to life. By the time the box girders slide into position, it's past midnight.
Everything went quite smooth today, so we hope tomorrow we can do the same.
With the lessons learned from the box girder lift, the rest of the segments go up smoothly. As the final piece rises into place, Singapore is already marveling at the team effort behind one of the world's most ambitious building projects. In just 3 years, engineers overcame seemingly impossible construction challenges, defeated marine clay, engineered ingenious design solutions, and survived the most debilitating financial crisis since the 1930s. As the finishing touches are put on the resort, the stage is set for an opening party, Singapore style. Those involved reflect on the project that has already far surpassed their expectation.
It's a bit kind of overwhelming, you know. I'm in the process of disconnecting the umbilical cord. It's not easy for an architect.
This type of project probably only comes around every 25 years or so. So it's been a lot of hard work, extremely challenging. I really can't imagine, I couldn't list the number of challenges we've overcome along the way to get to today.
Everybody is saying this is kind of a miracle, you know, never seen anything like it. And it's rewarding, it's nice.
The Marina Bay Sands, Singapore. Proof that with visionary design and engineering know-how, megastructures can still defy the odds and fulfill the wildest dreams.